hello. So we start off from where we finished the last time, and I slightly misjudged. We didn't actually need this theorem of the cube because I was hoping to use it to prove 2.2, but we didn't prove 2.2, so we only need 2.2. And then we proved the theorem of the square, and I also need one last funny fact about invertible shifts in this section, and then we will move on. So another notation. Is kind of standard in this theory. So given a Abelian variety x and an integer n, we can define a map powering to the power of n. So it is denoted like this, and in square brackets. So it's a map from x to x, which maps x to nx. So that's x plus x plus x. Okay, and the last claim here, corollary 2.4. If I take an Abelian variety x, invertible sheaf L, and an integer n, then this corollary tells us what the pullback by this and map looks like. And this is going to be something like this. So that's L tensor power to n times n plus 1 over 2 tensor with pullback by the inversion map of L n times n minus 1 over 2. That's the last thing will be here.
Tensor power, right?
Tensor power, yes. So that's L tensor because itself this we proceed. Let's first consider the case of the non-negative n. So first, n is non-negative. The cases n equals 0 and n equals 1 are easy. Right, so for 0, both of those are 0, so that's trivial on the right hand side, and on the left hand side that's the pullback by constant map, that's also trivial. And for n equals 0, that's just L, and here we have 1, here we have 0, so that's also L. So take n at least 2 and apply 2.2. For 3 maps, f being n minus 1 power, g just the identity, and h is minus 1, which is, by the way, just the inverter, right? And so if we write this equation in this case, what do we get? So the sum of all 3 would be what? What would be the map when I sum those 3 maps? So I map x to n minus 1, x plus 1, x minus 1, x, and I get f. Yes, f, so n minus 1. So n minus 1 pullback of L is isomorphic. 3 sums of all pairs, so f plus g is n. Tensor with f plus h is n minus 2. And g plus h is just 0. That's constant map. And those three guys are just n-1 pullback of L inverse times 1 pullback of L inverse times -1, so that's iota pullback of L inverse. Okay. And now what we need here is this thing, and we move everything else to the left hand side, and so what do we get? So pullback of L. What do we have here? We have this and this, right? When I move to the left hand side, I remove this V. So that's going to be what? That's going to be n-1 pullback L squared, right? And then n-2 of L inverse, right? That's strange, but okay. This one is pulled back by constant back, so that's nothing. This one is pulled back by the identity map, so that's just L. And this one is pulled back by iota L. Okay. Let me just check just in case if this is right. So, and then we do what? I prepared a bunch of exercises for my lovely listeners. That would be the first one, and I enumerated them just in case you will solve them and you will have some troubles and you will want to ask me about them. So check that induction works. So apply induction and just remove all the brackets that you'll get, and this should be something like this. Check that induction works, and for negative n we do what? We can say that this pullback by minus n is just the combination of iota inverse with n. And probably here you will need this contravariance of functors. And that's how you can prove this. Okay. So that's everything for invertible shifts. Now let's move to some interesting stuff. The third section is about projectivity and divisibility. Let us fix some Abelian variety X. And let us define this thing for a real divisor D. We define this H of D. Which is just the set of point x in X capital such that the translation of D is D. So this is a subset in X, and this is a closed subgroup. And that's pretty easy, but just in case, an exercise to check that it's a subgroup.
Subgroup?
Subgroup.
But this is just a stabilizer.
Yes, this is just a stabilizer. You can also prove that it's closed, but I don't really want to waste time on this. Now let me state a theorem which I will not prove it, but which I will use. So again, take a divisor D, which is effective, and consider the corresponding invertible sheaf. Then the following are equivalent. So the first one, L, is ample, so that sum its tensor power defines a closed embedding into projective space. The second one is this guy h of d is finite. And there's also a third, k of L is finite, but we will define this k of L later. We don't need this yet. Defined later. Okay, so that's a theorem. We can prove this, but it's some kind of tedious work, and I don't want to do this. I want to prove the corollary. What we can deduce from this theorem, of course, we can deduce that Abelian varieties are projective. So X is projective. Well, of course, how do we prove this? We just need to find an ample divisor or an ample invertible sheaf on X. And use this criterion with h of d. And what do we take as our divisor? We just take an affine open neighborhood of the identity. So take affine open, so neighborhood of the identity. You can always do this, and there's a general fact: X is smooth and complete. So an affine open subset in X always has complement divisor, support of a divisor. So X minus U is a support of some effective, we may assume, effective divisor.
But for this, you don't need to hold those conditions, right?
Sorry, what?
To claim this, you don't need neither smoothness nor completeness.
I need smooth. I need normality, I think. At least normality.
Okay.
No, actually it's continuous.
I'm not so sure. Okay, so. Well, it's still smooth and complete, and it's still. We still can use it. Okay. And I just claim that this is an ample divisor. So you just basically take any affine open in X, and its complement is going to be a support of an ample divisor. Right, so let us show that this h of d is finite.
Do you take D to be just the sum of its components?
Oh, I can do this, yes. I can just take the sum of the components. But I think it doesn't even matter. Just so that this holds.
So you can take any linear combination?
Yes, pretty much yes. Okay, so take a point. I just erased the definition, right? Take a point x in HD. So that's the stabilizer of D. And since it stabilizes D, and it's a translation, it also stabilizes U, right? So dx of U equals U. Right? So, but since we have an identity in U, we have what? We have x in U. And so we have an inclusion h of D is contained in U. And what do we have here? We mentioned that this is closed, so this is complete. And this is affine. Well, it's complete, but it may not be a variety, it may be reducible. So that's just implies that its dimension is 0, right? So it's fine. Okay, is it clear?
Could you please repeat? So what's going on here?
So I want to show that this thing is fine. Okay, I take a point in this h of D,
Which is the stabilizer?
which is the stabilizer of D. U is the complement of D, so x also stabilizes U. Okay, so, but since we have an identity in U, so there's some E, and I apply x to E, I get x plus E, which is x. So x in U.
Yeah.
Okay. So what do we get? We get every point in h of D is contained in U. But this thing is closed in x, so it's a complete thing. Maybe reducible, but complete. And this is affine by definition. So we have something which is complete, containing something which is affine. So this is just a finite set of points.
Okay, thank you. It's clear.
That's about projectivity and about divisibility. We have this. So for any integer n, at least one, the kernel of this map n is finite. By the way, did I mention that this map is a homomorphism of algebraic groups? Since it's Abelian, it's a homomorphism. Is finite and n is surjective. So in particular, x is divisible. Divisible group, which means that for any element there is we can take its nth root. For any element in any n, we can take its nth root, and this is exactly means that this map is surjective for every n.
In the additive notation, you just can divide by n.
Yeah, divide by n, yes. Okay, proof. So we have what? We have this map, n x to x, and x is a complete variety. Since it's complete, its image is always closed. And I guess by dimension of fibers theorem, it just suffices to show that this kernel is finite. Right, because otherwise, if it's not surjective, it is mapped into some smaller closed subset, so we have positive dimensional factors, right? So now we check that this kernel is finite, and we apply one of these funny invertible sheaves facts. So we just proved that X is projective, 3.3, so we can find an ample sheaf. Ample L on X. Okay. We can take pullback by n of this ample sheaf, and it's going to be trivial on when we restrict it to the kernel, right? Because why? Because that would be a constant map, right? We have kernel inside X, and we are mapping this to X. And of course, this composition is a constant map. So when we restrict, we pull back by this inclusion, so we get pullback in overall pullback by a constant map, so that's trivial sheaf. But on the other hand, we proved 2.4 with this tensor powered stuff. So we have this pullback isomorphic to L tensor n plus 1 over 2 and iota pullback L and n minus 1 over 2. So L is ample, and every tensor power of an ample is again ample. So this one is ample. And here we have tensor power of ample, which is ample, and a pullback by an isomorphism, so that's again ample. And this old stuff is the tensor product of two amples, again ample, so that's ample. The restriction of an ample is ample. Kernel. And now we see what? On kernel we have a sheaf which is both ample and trivial. When can this happen? Only when the dimension is 0, right? Ample and trivial. So basically when 0 divisor defines an inclusion in projective space. No, that's only true for a point, right? So dimension of kernel is 0.
So could you please explain why is it?
Come again?
Could you please explain? So what happens if it is not a point?
Okay, what happens? We have a complete variety. We have 0 divisor, and we have defined by this 0 divisor a map into projective space. But this map is what? It's mapped into P0.
So,
but this is ample, so this is an inclusion, so X must be a point. But in our case, it's reducible, so it's just finite set of points.
yeah.
That's it, right? Yes. That's it. So in particular, Abelian varieties are divisible groups. Okay. And a couple remarks here. So denote G equals dim x. And it can be proved that in general. So in fact, in general, this kernel has no more than n to the power of 2g elements. And moreover, if characteristic of our field does not divide n, then it can be shown that this kernel is the group. So there's equality in this case, and this kernel is just the group n over nz to the power of 2g. Okay. And maybe a definition here. So a homomorphism f from x to y of abelian varieties is called an isogeny. So if either of two equivalent condition holds, if one of two equivalent conditions holds. So either f is surjective and finite kernel, or they have equal dimensions and finite kernel. Okay. And there are also a couple of other equivalent conditions. And so, for example, this map is an isogeny. And for abelian varieties, it can be proven that being isogenious is an equivalence relation. So if f is an isogeny, then there exists isogeny in other direction.
But still it can be not an isomorphism.
It can be not an isomorphism. Well, for example, we are going to define dual abelian varieties, and abelian varieties are rarely isomorphic to its dual, but they're always isogenious. So, next section, Picard group and dual abelian variety. And we start with a motivating example. So what do we have for elliptic curve? So let's see the elliptic curve. So we have a homomorphism. Just like for every curve, we have a degree homomorphism from the group of Weil divisors to Z, right? just the degree of a divisor, which is we set degree of a single point equal to just 1, right? So P is a point which is a prime divisor, maps to 1. And so linear combination maps just to the sum of the coefficients. And the standard fact is that every principal divisor has degree 0, so this in fact gives us a map from the Picard group over the class group. Right. And for example, for projective space, this would give us an isomorphism, but in general this degree has a kernel, so there are 0 degree divisors which are not principal. And this is denoted by pic 0, so that's the connected component of the Picard group. So pic 0 of C is the kernel of this degree.
So what do you mean by pic 0?
Kernel of the degree.
By definition.
By definition, that's just all the divisors in the classes of divisors of degree 0. And in this case, we have the quotient pic C by pic 0 is, of course, just what?
Z.
Just Z. And because this map is clearly surjective. Okay, and for elliptic curves we have this nice thing, which is in fact we can define the group law on elliptic curve not by this geometric construction which I gave in the previous talk, but by just the operation on pic 0, because we have this map, the map C to pic 0 of C, which maps a point P to the divisor P minus E identity. That's minus inside pic 0. So this map is an isomorphism of groups. So you can just induce the group law from its Picard group. And we kind of want something similar in the general case for an arbitrary abelian variety X. So let's try and do this. We fix abelian variety X and an invertible sheaf L on X. So first we define this.
So can I ask you, in this way, do you want to define an algebraic variety structure with pic 0?
We basically define this because we have an isomorphism, so it's a bijection, so we can shift the algebraic variety structure from C to pic 0.
So is it really what you do?
Not yet, but I will in particular build this. So yes, you can note that we basically turned pic 0 in this case into an algebraic group. And we will, if I have the time, we will do this in general. Okay, so we start with this phi L. Phi sub L is a map from X to pic X. How does it work? It maps a point X to this class of sheaves. So pull back by dx of L, tensor with L, LV. And you can see the analogy with this when you take what? When you take L. So what is an invertible sheaf? It corresponds to a divisor, so if we take L just corresponding to the point E, and we also need to shift signs so that it works, so maybe change minus X for X, And then we'll get just this thing, because it will be e plus x, which is x minus e. So that's the generalization of this formula. And another exercise here. So deduce that phi sub L is a group homomorphism. And now we need another of these strange sheaf facts. So that was theorem of the square from 2.3. So theorem of the square basically tells us that this map is a group homomorphism. And here, now we define K of L, which we mentioned in theorem 3.1, I guess. Now we can define this. This is just the kernel of this phi L. So it's a subgroup in X. Subgroup. And in fact, it's closed. It's even closed.
But shouldn't it follow from the standard fact?
Or what?
Ah, okay, I see.
This is from so-called seesaw theorem, which I do not mention here. Seesaw means качение. Okay. And another exercise.
So you mean that this is not zero?
This is, yes, this thing is horrible. Given a divisor d on x, show, so we have a divisor, we have this h of d, and we have the sheaf corresponding to the divisor. So we have L and we have its k. So it turns out they're related like this. H of d is contained in the corresponding k of L. So Lx of d. And for this, maybe you will need to recall we discussed this previous time. So the shift of a divisor is related to the pullback of sheaf like this, minus x of Ox of d. Okay. This K of L, in particular for ample L, it's finite by the theorem which we formulated earlier. And now we can define peak 0. We can define peak 0. That would be all classes of sheaves in Picard group such that phi of L is 0 map. Phi L is 0 map. So it maps every point to a trivial sheaf. Or in other words, we can rewrite this as what? As classes in Picard group such that the kernel is whole X. Okay. And it's also not so hard to show that this is a subgroup in peak because we can just show that in general this map which is defined by phi, so we have phi, we did what? For every sheaf we defined a homomorphism from X to P, right? for each L, I have the map phi L, which is a homomorphism from X to peak, and this is a homomorphism. This is a homomorphism of groups. So in particular, this peak 0 is its kernel, right? So peak 0 equals its kernel, so it's a subgroup.
So again, what is the map?
What is the map? Here.
Ah, yeah.
For each one, we defined a map. So we have a map from peak to X to peak.
And also a question about the definition of this peak 0. So
Yes.
does it directly generalize the case of the elliptic curves?
Well, as you can see, not quite directly. It's kind of intricate, and you will see, well, it's kind of complicated because we will now actually mention that, so we have this map phi L from X to peak X. We use this to define peak 0, and now we will actually give it as an exercise to show that this map is mapped inside peak 0 actually. So you see that it goes up and down, and I'm not sure how to directly correlate this with the elliptic curve case. And here it goes, another exercise. Show that, well, as I said, the image of each phi L is actually contained inside P0. And if L was from peak 0, then we have a funny property that the pullback by M is again in peak 0. So it's like even more than a subgroup, it preserves these pullbacks. And another thing I want to mention here, which we will not use, but I think it has to be mentioned, the neuron severity group. Severity group. So NS of X is just this quotient peak by peak 0. Remark. This thing, NS of X, is a free, finitely generated Abelian group of rank at most 4 times dimension of X squared. So this was proved by severity over complex numbers and by neuron over arbitrary fields. This we will not prove, of course, but you can show exercise that it's torsion free. Is torsion free. Okay.
There's a particular case, right?
As a particular case of what?
Of the previous statement.
Of course, it falls from this,
Yes.
but I mean, we exercises to show this not using this theorem, just use the definitions. Okay, and now we can define this dual abelian variety, not define but construct. Actually, we will not define it, but we will construct it. Okay, there exists so-called dual abelian variety. X hat, I will denote this. Well, it is defined by some universal property, but it's kind of complicated. I don't want to formulate this. It's in terms of families of invertible sheaves, or maybe known better as divisorial correspondence. I will not talk about this, I just state some nice properties that it has. So it has the same dimension, and I said before, these are even isogynous. It defines an abelian variety structure on the peak zero, so there is an isomorphism. There is an isomorphism, let's call it psi, from x hat to peak zero of x. And some nice property is that for any ample, maybe I should use other word. So for any ample L on X, there exists a unique surjective homomorphism that's denoted by like this, from X to X, such that psi with this is equal to phi delta. Okay, maybe draw a diagram. So x to x, and then to peak zero, and here phi L. Phi L, L lambda and psi. And maybe before we construct this, a couple of comments. Well, an example, of course, for elliptic curve. Can you guess what is the dual to an elliptic curve? So dual should define a group structure, an algebraic variety structure on peak zero, right? Elliptic curve already defines an algebraic variety structure on peak zero, so the dual to an elliptic curve should be what? Itself, right? So again, zero chance of another example. And maybe a definition here. A polarization of abelian variety X is a surjective homomorphism from X to its dual. Right, so a polarization for a projective variety is usually a choice of an ample sheaf, but by this property, to choose an ample sheaf means exactly to choose a surjective homomorphism. So for abelian varieties, polarization usually means a surjective homomorphism like this. Okay, so proof. Idea. how can we construct this? Actually, it's not so hard if we have this fact. So it can be shown that if L is ample, then actually this map phi L is surjective. Big 0, so surjective. So ample divisors give rise to a surjective map. And now we can just do what? By this criterion of ampleness, we know that K of L is finite, right? Which we used to prove projectivity. We know K of L is finite. This homomorphism is surjective. And then we just do what? We can just define x hat to be the quotient of x by this finite group K of L. And everything works. Right, so this is a projective variety, this is a finite group of its automorphisms, and this quotient always exists, and it also gives rise to a projective variety.
So clarification, also dual arbitrary is uniqueness.
Is unique? What do you mean unique?
For x, there is only one arbitrary.
But we haven't defined a dual variety.
Because it's theorem.
That it exists. It has these properties, but we haven't defined it. Because, as I said, it is defined in terms of some universal property, which I don't want to formulate because it's kind of like big. It's about some families of invertible sheaves, so this X should parameterize them, and so that's the definition. So basically, we don't have the definition, but yes, it's unique if you define it by this not mentioned property.
Dual to dual is just x.
And dual to dual is just x. And I think when you do this theory, you want to have some kind of like pairing between x and x. But you can't define it in terms of just Abelian varieties, and so that's where motifs come from. So it's basically to define pairing for x and x dual. That's enlarge the category and work with motifs. And I just have a little bit of time. So maybe quickly we move through Jacobian of curves. So let's just state what's going on. So now X is a smooth projective curve of genus G. Theorem 5.1. There exists an Abelian variety G, or G of C, such that the dimension of G is G, the genus of J is G, and it also defines a variety structure on X0. So that's basically a generalization from elliptic curve to arbitrary curve. And in this case, big 0 is defined because it's a curve, so that's just divisors of degree 0.
So, we do not not C, so probably we want to
X, yes, thank you, that's X. Of course, example for Pn, P1, I mean, G is what? A point. And for elliptic curve, that's basically the same as the dual. G is X dual and it's X. Of course, I don't have time to discuss how it's constructed, so maybe just a couple of facts. So maybe just to mention some interesting stuff. So we have this Jacobian, and the first question is every abelian variety is a Jacobian? The answer is no, but if I have an abelian variety A, then there exists a Jacobian variety J such that it surjects into A. So basically every abelian variety is a quotient of a Jacobian, and there is an open question.
So Jacobians they form just a subclass of all abelian varieties, no?
Yes, that's a subclass, but every abelian variety can be subjected to by a Jacobian. And I think it's still open, so let me start with an abelian variety. I can subject the Jacobian, then I can find a kernel, then I can find its identity component, then I can also subject it to the Jacobian, right? And I can go on and on. And the question is, does there exist a finite resolution of abelian variety by Jacobian varieties? So something like this. Well, it's not exact sequence because when we have kernel, it's not an abelian variety yet, because I want to take its identity component, right? So it's not an exact sequence, but we still can ask this question whether this kind of resolution exists, and I think it's still open. Whether I can resolve an abelian variety by Jacobians. And the famous theorem by Torelli. If I have two smooth projective curves, C and C prime, then they are isomorphic if and only if Jacobians are isomorphic, but with some but their canonical polarizations are isomorphic. Canonical polarizations. Well, there's like, for Jacobian there always exists one nicely defined polarization. It's called canonical. So there's this theorem which states that two curves are isomorphic if and only if their Jacobians are isomorphic with their polarizations. Okay, I have no more time, so that's all. Thank you very much. Здесь? Здесь.
Так, галочками и края.
Здесь. Нет, ну, в смысле, поляризация нам задает вложения, вот эти вложения должны быть одинаковые.
Questions?